Hi, everybody. It's a pleasure for me to be here, and I'm very happy to see so many of you showing up for this great conference. So I know that most of you have come for the data analytics part of this conference, and my talk is about quantum technology. That doesn't quite fit, right? Well, if we start by asking ourselves, what's been driving this revolution that we've seen in data analytics and machine learning? Is it the algorithms? It's not, because most of these algorithms that are so successful nowadays, they were actually known since the 1980s. So it must be something else. And in fact, the answer is that it's mostly driven by the revolution in hardware. Our computational power has grown a lot, mainly due to GPUs now being used not just for graphics processing anymore, but for number crunching in other contexts, and also the TPUs mentioned by Hans, especially developed for applications in machine learning. And so to make the connection, my talk is going to be about a potential future development, a new technology that might someday help us to actually reach a new level of computational power. And the amazing thing is that nature seems to tell us that the way we process information now is not the best we can do. So without further ado, let me start my talk. Quantum technology is by now quite a big field with many subfields. And today, because of lack of time, we will focus mainly on only 3 of these parts. First, I will spend some time discussing quantum computing, and then we will see some applications of this technology to cryptography. So quantum computing also originated in the 1980s with people like Richard Feynman, a famous theoretical physicist, who in the later years of his career started wondering how we could address a very vexing problem to any quantum physicist, which is the problem of trying to simulate a complex many-body quantum system such as encountered in quantum chemistry, for example. The problem is that the dimension of the space where the system lives essentially grows exponentially with the number of constituents, and all our classical computational tools are not able anymore to simulate this or keep this in memory. And so he asked the provocative question of whether we shouldn't start thinking about building a quantum machine to simulate another quantum system. And that basically was the birth of quantum computing, which since then has come a long way. As you can see, for example, by looking at covers of some of the more prestigious scientific journals, which now regularly feature articles about quantum computing. But of course, quantum computing is not just something that is of interest to academicians. It has now also triggered the interest or imagination of a wider audience. I'm pretty sure that some of you at least have heard about quantum computing, perhaps even read some popular articles such as this one in Time magazine. And it's also no longer a small part of the whole research landscape as shown here. This is a bit outdated from 2015, an estimate of the total worldwide investment in quantum technologies. It's about 1.5 billion per year, and you see here the major players are the US, Europe, and China. And if you look at the announcements made last year by these governments, it looks as though this trend is really set to continue for a while. So we have, for example, the European Union in the center that announced last year the quantum flagship program funded with 1 billion over 10 years to foster what they call the second quantum revolution. What's really interesting for me as a scientist is that progress is now currently not driven anymore by academia, but by the private sector. And here is a very partial list of some companies that are involved actively in this research. And you can see here there are some major data analytics players like Google, IBM, Microsoft, and then hardware companies such as Intel and Honeywell that are all part of this effort to build a quantum computer. Now, in order for me to explain a little bit more what quantum computing is all about, and hopefully also what it is not about, I want to try to introduce what in my mind is the key aspect of quantum mechanics that one needs to understand to appreciate what a quantum computer does. And this is what is usually called particle-wave duality, is this weird property of quantum systems that they can be both particles and wave at the same time. A beautiful experiment that illustrates this is as follows, as shown in this cartoon. If you have a source of quantum particles, think electrons or photons, or even molecules, as we will see in a moment, and you shoot them at a wall which has these two openings here, excuse me, I don't have a pointer, what you will see on a screen placed in the back is impacts of individual particles. And that's exactly what we would expect from classical particles as well. We never measure half a particle or a particle spread out, but we just get very individual impacts. However, if you keep measuring, eventually you will find, when you look at the intensity, that this intensity is an oscillating function along the coordinate of this screen. And this is not what we would expect for classical particles. There seems to be some kind of wave phenomenon going on, as if each particle, when it goes through these two openings, it kind of knows about both openings at the same time, as you would have if you would do this experiment with waves, like water waves or light waves. Now, in order to make sure you believe me that this is not just a cartoon invention of mine, here is a movie of exactly this experiment, which was done in a collaboration of, I think, the University of Basel and Vienna, where they use as quantum particles these huge molecules, which have this unpronounceable name, phthalocyanine. And you see on the left, they're quite huge molecules. So these are not just these fuzzy particles, photons or electrons, whatever that may be. This is a real chunk of matter. And they were able to cool it into a quantum state and then perform this experiment. This is what we're going to look at here, accelerated a little bit. So you see these individual impacts. It's going very fast. And now I'm skipping some frames. And you kind of start to see the emergence of these patterns here. You very nicely see these interference fringes. So this is a real effect happening in nature. So what does this all have to do and how, with quantum computing and how do we understand this within quantum mechanics? On this slide, I'll do a little bit of math, but don't be scared, it's not that much. And I will try to illustrate things using pictures as much as I can. So quantum mechanics essentially is a prescription that tells us how to compute probabilities of measurement outcomes. And in this context of this double slit experiment, a measurement outcome simply means an impact of a particle on the screen at some position x. So quantum mechanics tells us that if we want to calculate the probability of observing a particle at a given position x on the screen, what we need to do is to sum over all possible paths that the particle can take from the source to the screen a certain quantity psi, this funny character up there, which is a complex number. And then once we have done the sum, we take the modulus of this complex number and square it, and this is the probability of observing the impact at that position. Now, if you don't remember what a complex number is, just think of it as this green vector here. It's a little arrow pointing in some direction. And with this tool, we can now follow through what happens to one of these quantum particles as it goes through this experiment. So first, it starts here on the left as this purple, orange dot. And its state, which is this psi, is pointing, let's say, upwards. Then, as the particle travels towards these two openings, the state will rotate. This is because the phase of this complex number is essentially a function of the distance traveled by the particle. Now, up to this point, the distances on the blue path and the red path are the same, and therefore the arrow points in the same direction. But after that, you see that the blue path is shorter than the red path. And that means that as you keep moving along, the arrows might point at the end in exactly opposite direction at a certain point on the screen. And if that happens, our prescription tells us that now the probability of measuring a particle at that position is 0, right? This is destructive interference, as we say, because adding two vectors pointing in opposite direction obviously gives you 0. If you move a little bit on the screen, you might end up in a situation where instead the arrows line up in the same direction, and then you get a finite probability. And if you keep moving along the screen, this will alternate between regions where you have particles and regions where you don't. So this is basically how quantum mechanics explains this. Now, what does this all have to do with quantum computing? The reason I brought this is because, for me, if I were asked to say what, in a sentence, what is quantum computing, I would say this. Quantum computing is all about exploiting these kind of quantum interferences to give the wrong answers to the problem you're trying to solve very small probabilities, while at the same time enhancing the probability of the right answer. That's still very abstract, so I'm going to try to walk us through one concrete example of a quantum algorithm. This is known as the Growver search algorithm. It's one of the two key quantum algorithms out there. And the setting is very simple. Suppose you're given a phone book, and you're given a phone number and asked, whose number is this? Now, classically, to solve this problem, if there is no structure in the phone book, the best thing you can do is to open the phone book, the first page, look at the first number, compare it with the one you're given, and continue until you hit the right number, here in green. And of course, if you would repeat this many, many times with many phone books, you can clearly see that on average, you will need about n½ trials, where n is the number of phone numbers in the phone book. So in complexity theory, we say that this optimal solution here scales as the size of the phone book. So it's big O of n. Big O just means we don't care about multiplicative or additive constants. And what I'm going to show you next is that if you have a quantum computer, you can actually do better. You can solve this in faster than order n. So the starting point of this algorithm is that you need to prepare your phone book in a very special state, which is depicted here. Let me walk you through what this means. So I try to use the same notation or pictures as in the previous slide. So this string of boxes, the first one, for example, represents a phone book which happens to have the phone number you're looking for on the very first row of the first page. So that's the lucky one. The second one similarly has the phone number on, let's say, the second row of the first page, etc., all the way to the last little snake here, which has the phone number you're looking for at the very bottom of the last page. So that's the very unlucky phone number. Now, the crucial thing is that quantum mechanically, you can prepare your phone book in a state which is simultaneously in all of these configurations. And just as in the classical case, how many, let's say, qubits, quantum bits do you need to realize this phone book? Well, you only need a logarithmic number in the number of phone numbers. So if you have, let's say, a million phone numbers, you need about 20 qubits. Each component up here, as I said, represents one of these cases of phone books. But the important thing is also that it also represents what would happen to your phone book if you were now to measure at this stage. So you have prepared this state, and now you make a measurement, you make a query. Basically, you open your quantum phone book, you look at the first phone number. If you do that, what happens is that you will collapse this state to one of its components at random. And what is the probability of getting any of these answers? Well, it's given by this number here, the 1 over square root of n, multiplying the whole thing. That is exactly our psi that we had before. Actually, the probability is 1 over square root of n squared. Remember, we had to take the square to get the probabilities. Okay, so at this stage, we haven't really gained much. But now what I'm going to do is I'm going to try to explain to you this Growver algorithm. And for this, I would like to change the notation slightly. So I'm going to simply isolate this lucky phone book, and I call it the right state from now on. And all the rest, I'm just summing it up, putting it together into this wrong state. And the reason I do this is because, again, we can now use a nice graphical illustration of our phone book. We can simply view it as a vector, this black vector, DB, database, which in this original state points very much along the wrong direction, right? Because you see this factor multiplying wrong is roughly 1 for large n. And it's a very small number for the right direction. So this angle theta, in fact, is just 1 over square root of n. And so I can also write this state like this with sine theta, which is a small number, and cosine theta, which is close to 1. And in fact, I'm even going to simplify it further. I'm going to just draw a little pictures kind of illustrating that in this initial state, if we were to measure, we would very high probability get the wrong answer. That's why we have this high blob and the small blob in front of the right state. Now, what Growver managed to do is he found a way to manipulate these m qubits in a way that we can rotate this state by a step of size 2 theta into the direction of the right state. This is exactly what I said in this one-sentence explanation of quantum computing. We're trying to shift the weight of this probability towards the right state, away from the wrong state, without making any measurement. That's important. Now, if we keep doing this, we do exactly that. We shift this probability and end up, ideally in this case, where now we have a very large probability if we make a measurement, if we open our phone book and look at the number, to get the right answer right away. Now, the crucial question which remains is, how many steps did we need to achieve this? And this we can easily answer from this picture. All we need to do to estimate this is take the full angle between right and wrong, which is 90 degrees, and divide it by the size of one step, which is 2 times theta, and theta is 1 over square root of n. So if we divide by 1 over square root of n, not surprisingly, we get, excuse me, that's on the next slide, we get square root of n. So we can achieve this, find a solution with very high probability in order square root of n steps instead of n. It's a quadratic improvement with respect to the best classical algorithm. Now, I hope that you could more or less appreciate the power that this quantum interference gives us. And in fact, this is just one example. There are many more quantum algorithms known by now, and some of which give you actually even more impressive speedups, as we will see in a moment. This sounds very exciting, right? It is, but some people are also a little bit scared by this potential power of quantum computing. In particular, people who are in charge of cybersecurity. Quantum computers pose a security threat that we are still totally unprepared for. Okay, why is that? The reason is that one of the pillars of modern cryptography, known as asymmetric cryptography, which is the thing we all use to communicate securely with each other, relies on what is known as a one-way function. So basically, what is a one-way function is just a function that is easy to compute. Given the input, I can easily find the output, but it's very hard, given the output, to figure out what was the input that generated it. And this one-way function in this context is essentially used as a public key. That's also, why asymmetric cryptography is called also public key cryptography. So what you share with the whole world, including the person you want to communicate securely with, is just essentially the result of such a one-way function. And you're sure that even if an eavesdropper gets your public key, they will not be able to easily invert it to crack your communication. To give you concrete examples, SSL, which we all use every day when we go to an HTTPS website, for example, uses under the hood a one-way function which is known as integer factorization. What is integer factorization? Well, it's simply if I give you an integer number n, and I ask you to find the prime numbers p and q, such that multiplied together they give n. This is a one-way function. A simple concrete example, 15 is equal to 3 times 5. So 3 is a prime and 5 is a prime. That's the solution. So this is a trivial example. It's kind of not illustrating this one-way property. But if I give you instead this number, this is a large integer, and I ask you to do the factorization, I'm actually pretty sure you won't be able to do it in my lifetime. Unless tomorrow you have a quantum computer. And here's the answer. I had a little insight yesterday in the train, and I managed to do it. No, I'm just kidding. I didn't. I just generated these two prime numbers, which was fast with a simple piece of Python code. And in a few seconds, I got that number. So you see the one-way nature now, right? OK, and in fact, it's been estimated that for such a number, which is all these primes that are generated are 1024-bit semi-primes, it would take us about 2,000 years to factorize it. With the state-of-the-art algorithm and the classical hardware. And here is the scaling of this best classical algorithm. So just draw the graph instead of showing just the expression here. It's not quite an exponential explosion, but you see it's still pretty explosive if you look at the scales on the y-axis. Now, this was the status until this gentleman published a paper, Peter Shor. In 1997, he found an algorithm, actually many algorithms, that solve these factorization problems in polynomial time. And here's the graph showing the results. So the blue line is exactly the same as on the previous graph. I just changed the scale here to logarithmic scale. And the orange curve is the scaling of the Shor algorithm. And you see, for example, for a 100-digit number, 100-bit number, you get a 1 million times 1 million factor speed up. So that means extrapolated that for my if I use the previous number as a public key, if you have a quantum computer, you probably can crack this code in a matter of hours. So to summarize, quantum computing could put an end to asymmetric cryptography. And that's quite a big deal. Now, is that the end? Not quite, because there are other cryptography schemes that are in use, such as, for example, symmetric cryptography, where the idea is to use the same key for both encryption and decryption, in contrast to public key cryptography, which uses two different sets of keys. And if you analyze this with respect to its robustness to quantum computing, you find that in this case, you can still benefit a little bit by using a quantum computer if you're an eavesdropper. But basically, what you're using under the hood is the Growver algorithm, the one that gives you only a quadratic speedup. And so that means that if you want to use this symmetric cryptography and be safe in the quantum era, all you have to do is to double the length of your keys. So that's not that bad. But the problem with this scheme is that you cannot easily use it for communication because of the reason that you have to share a private key, the one that is used for encryption and decryption. And this exposes symmetric cryptography to what is called man-in-the-middle attack, which is, as the name indicates, the problem that if you have two parties in green and blue that want to communicate safely, but there is also this eavesdropper in the middle, then if he intercepts the message containing the key, he makes a copy of it, sends the original along, then our two parties there, they have in principle no way to detect the presence of this eavesdropper, and so they can never be sure whether their key is now compromised or not. And here, surprisingly, quantum mechanics comes to our help. And this is because of two fundamental properties of quantum systems. The first one being that when you observe a quantum system, as Beat mentioned in his introductory speech, you actually modify the state of the quantum system. And this is nothing to do with our clumsiness in doing the bad kind of measurements. It's a fundamental property of quantum mechanics, also known as the Heisenberg Principle. And this basically means that the eavesdropper cannot go undetected. To be true, you need also the second property, which is that a quantum state cannot be copied without destroying the original. So these two things together make it impossible for an eavesdropper to remain undetected, and that means you can now figure out ways to share a key safely. And this is exactly what these two gentlemen, Bennett and Brassard, had done in 1984 by introducing this, the following protocol for sharing a key in a provably secure manner. So what you need on the center side of Alice is a photon source, which produces one photon after the other. And you also need two separate sets of polarizers, one along the horizontal vertical direction, and another set along either the 45 degrees or minus 45 degrees slanted the polarization direction. What Alice then does is that she takes her photon and decides randomly which setting to use. And then she perhaps decides, okay, the first photon, I'm going to choose the horizontal vertical setting, and I'm going to use the zero, the horizontal polarizer, send my photon through it, and then basically she sends this photon to Bob. And she does that many, many times, again, randomly choosing for every photon which of these four cases she wants to use. Bob, on his side, he has two settings of detectors, one corresponding to the horizontal vertical setting, and the other one to the slanted setting. And for each photon that he receives, he basically chooses at random one of the settings, and then he records two things. One thing is the setting that he used, and the other thing is the result of the measurement. He just writes them on a piece of paper. They do this many, many times, sharing many photons in this way. And after a while, Alice decides, okay, that's it, and she sends an open message that everybody can read to Bob, saying for each photon that she sent, which is the setting that she used, but not whether she prepared it in 0, 1, but only whether she used the slanted or the horizontal vertical setting. And then Bob, when he receives this information, he goes through his record, and for every case where the settings match that he chose for the measurement and that Alice chose for the preparation, he keeps the measurement result as a valid bit. In case they don't match, he throws away that bit. And in doing so, they end up with a sequence of valid bits, which now they are certain are the same on both sides. And this is because if you measure twice a photon on with the same polarizer, you're guaranteed to get the same answer. And so this kind of devices actually already exists. This technology is much more mature than the quantum computer, and you can order it, for example, from a Swiss company, ID Quantique, based in Geneva. And what I would like now to do for the last 5 or so minutes of the talk is to talk a little bit about the other side of quantum computing, the hardware side that I was saying is actually the more important side, to try to give you a bit of an idea where we currently are, what is the state of the art. So this blue graph up there is what is called a superconducting quantum processor from IBM in this case, which features 7 qubits. The 7 qubits sit at these slightly darker square regions, and actually the qubit is formed by these structures which are enclosed in this red box, which consists of an inductor, essentially. This meander is nothing but an inductor, and the capacitor, which contains a nonlinear object known as a Josephson junction. But without further details, what's important is that this oscillator, by cooling it below the superconducting temperature, is put into a quantum state. So we have a quantum oscillator. And this means it has discrete energy levels, and the qubit this effective two-level system that we need to encode information, is realized as the two lowest energy levels of this oscillator. Interaction between the qubits is mediated via microwaves, and this is what you need on the right-hand side. This whole apparatus is what you need to basically cool this chip down to very low temperatures and also to bring down all these microwave signals. So this is where you see all these cables. They are basically coaxial cables bringing down the microwave pulses. And this whole thing is put into a dilution refrigerator, which reaches very low temperatures of about 100 millikelvin. To give you a reference point, outer space has an average temperature of about 2.7 Kelvin. So we're here much colder than outer space. Now, why is it so hard to build a quantum computer? The main challenges are summarized here. So the first one is that, as we have seen, quantum computing is all about exploiting quantum coherence, but its property turns out to be very fragile in the sense that as soon as your qubits interact with other degrees of freedom of the environment, they will lose this quantum property and become classical bits, which are essentially useless for quantum computing. This is, by the way, also the reason why we don't see these so-called Schrödinger cat states in our everyday experience. We never see a cat dead and alive at the same time because it continuously is interacting with the environment and its coherence decays on timescales which are immeasurably small. Now, you could say, well, why can't we just isolate our qubits more and more? Wouldn't that be possible? I guess it would, but the problem is you also need to be able to control the qubits because we, the user of the quantum computer, are classical, and so we need to have a channel to this quantum world down there, and by doing so, we open up, again, the first problem of decoherence. So there is a trade-off to be found between these two. The last challenge is scalability. We've seen an example of a quantum processor that lives in very extreme conditions, ultra low temperatures, and it's far from obvious how to scale this up from these 7 qubits to, let's say, 1,000,000 qubits. Now, to paraphrase Ike Chuang from MIT, quantum computing is no longer a physicist's dream, but it's an engineer's nightmare. And just to give you a scale of the nightmare, it's been estimated that in order to reach what is called quantum supremacy, so the point where in history we can demonstrate that by solving a problem that cannot be solved anymore by the most powerful supercomputer, that indeed quantum computing works, this would require on the order of 50 qubits, because we have very powerful supercomputers, which can simulate 50 qubits, right? But beyond that, it's kind of not possible anymore. And so if we could reach this, that would be a first milestone in this endeavor. And that's the challenge, but 50 from 9 to 50, it's probably still doable within a few years. The second line is a bit more humbling. In order to break this 1024-bit code with the Shor algorithm, we would need about 1,000,000 qubits. And that is very challenging. So to conclude, let me come back to the question I posed in the title. Should we fear quantum technology, or is it something we should embrace and look forward to? I definitely think it's the latter, because, of course, solving some very hard problems for which we do not have classically efficient algorithms more efficiently is certainly going to open up many new opportunities. With respect to quantum cryptography, I'm not too worried either, because when you think about it, cryptography is probably as old as humanity. And I'm sure the Babylonians didn't have the computational power we have today, and yet cryptography has always kept up, or even with the developments in technology, and I'm sure the same will happen for quantum computing. And finally, if you're personally in charge of cybersecurity, you shouldn't have sleepless nights right away. The revolution is not yet here, but you might want to consider thinking about it. And of course, if you do so, we at swissQuant would be happy to assist. And with this, I thank you very much for your attention. I'm looking forward to the next talk.